I'd like to thank the organizer for giving me the opportunity to talk about our work. And I'll be talking about probing nature of dark matter using strongly lensed gravitational waves. So the work is done in collaboration with Saswat from IUCA, Teja from UCSB, and Ajit from ICTS. So this map is the upper map is familiar to all of us. So this is the cosmic background radiation map. And it is a temperature map. The average temperature is around 2.7 kelvins, and on top of that there are fluctuations. You can see the hot and cold spots. So these fluctuations are in the micro Kelvin scale. And the lower plot is the plot from the Galaxy Redshift survey. So this shows the large scale structure what is see today. So these contents are almost 3 lakhs galaxies. So each point on this plot is the galaxy. So our standard model of cosmology is the dark energy dominated cold dark matter model, which is a 6-parameter model. And this model successfully explains the evolution of the universe from this stage where the fluctuations are very tiny on this microkelvin scale towards this clustered and filamentary structure what we see today. And also these observations from the low redshift and this from our local universe, this actually sets the energy budget of our universe. And you can say that the only 5% is the ordinary matter, and 26% of the dark matter, and rest is the dark energy, like 69%. So we don't know about this, which consists of the most of the matters. And this is the unknown matter, non-baryonic unknown matter. But this actually drives the cosmic structure formations and galaxy formations and holding these galaxies inside the clusters. But we know very little about this. So actually this standard model of cosmology explains almost all the observations. Those are done in large scale observations. But what about the small scales? So this shows the simulations of a CDM universe. So this shows the dark matter distribution around a Milky Way sized galaxy. And you can see the bright spots. These bright spots are high in density, so they can form the subhalos. So if you count up those number of subhalos, you'll see that there are 1,000 subhalos which have mass greater than 10 to the power 7 solar mass. So they can potentially host the galaxies. And here I show the observed satellite galaxies of the Milky Way, and you observe only 50. So there is a huge mismatch between the CDM prediction and what you observe. So this is known as the missing satellite problem. And also if we observe the rotation curve, the rotation curve is simply square root of GM by R. So the rotation curve of this satellite galaxies. So these data points you see, so this is the rotation curves from observations, and this black dashed line is what is the CDM predictions. So this depends on the density profile of the object. So CDM predicts a fall of 1 by R fall of near the central region, while the observation suggests that there should be a flat density profile near the central region. So this is known as the cusp and core problem. So there is a problem or the discrepancies from the CDM prediction and the observations. So to solve these problems, there are new dark matter models proposed. Also, there are these can be because this simulation is for only dark matter without considering baryonic physics. So within CDM, if you consider the baryonic physics and consider the feedback effects, this can be explained, but this doesn't rule out the dark matter model proposed to solve these problems. So just to give a summary, the dark matter candidates, so there are several dark matter candidates, those actually expands in mass scale like 80 orders of magnitude, starting from the elementary particle to the black holes and the massive compact objects. So this region is the cold dark matter region, and here is the warm dark matter, which mass is in the KeV region, and in this left region is the wave-like dark matter, which is ultralight dark matters. So warm dark matter is the, as this name suggests, so this has a non-zero thermal velocity. So it can actually freely stream through regions, and it has a free streaming mass scales below which structure cannot be formed. So it can erase structures at galaxy scales, and the mass is in keV range. So the current best constants comes from the observation of Lyman alpha forest. So there is a distance quasars that emits radio waves, and it passes through the neutral intergalactic medium, which consists the neutral hydrogens. So it can map the neutral hydrogens, and then through that we can prove the power spectrum, and it puts the constant around 6. So MWDM greater than 6.048 keV are allowed, less than are ruled out. Now this FDM is the fuzzy dark matter model. So these are wave-like dark matter. So the masses are 10 to the power minus 22 electron volt. These are bosonic dark matters. So which has a de Broglie wavelength around 0.4 kiloparsecs. So which is like size of the galaxy. So it can affect the structure formation at the galaxy scales. So I'm interested in these two models as this affects the structure formation in galaxy scale. So how can we probe with the gravitational waves? So we can probe through the gravitational lensing. So gravitational lensing, so if the GW passes through nearby some mass structure, galaxy scale masses, it produces two copies of the signal that will reach to us at different times. So there will be a time delay between these two signals, and one signal will be amplified, another signal will be demagnified. So if we have, and the time delay can be accurately measured due to the timing accuracy of our detectors. So if we have many detection of those, we'll have that accurately measured time delay distributions. And what is the probability of this occurring this scenario? This is, we compute the lensing probability to be around 1%. So 1 in 100 events is expected to be lensed. So there are 3G detectors proposed 3G detectors like Cosmic Explorer, Einstein telescopes. The event rate in the detection rate is very high, around 10 to the power 5 events per year. So if you consider 10 years of observations, then there will be millions events, and out of those, like thousands of lens DW is expected. So those can be a completely new data set and can be new probe to cosmology in dark matter. Here I'll tell how to probe this nature of dark matter. The lens mass we are considering is the 10 to the power 8 to 10 to the power 14, so 14 solar mass. So these are the lens mass we are considering. So we are not going below this 10 to the power 8 because that is the geometric optics limit. So this time delay actually depends on many things. Where the lens is, and where the source is, and what is the distance between these two, and what is the relative orientation between the lens and the sources. So how this nature of dark matter affects the structure formations. So this simulation is done in CDM. This is at redshift 15, and this simulation is considering a WDM particle of mass 3 kilo electron volt. And you can see the smoothness of this structure, because there are very less low mass structures. So if we count the number of objects of a particular mass and plot them like with respect to masses, this is the plot you will get. So as you can see, as the dark matter is becoming more warmer in the downward directions, there is a suppression in the low mass halos. And you convert this mass to a parameter called this velocity dispersion, which is simply square root of gm by r. And you can see the reduction in the numbers for this low sigma. And I plot this sigma to the power 4 dnd sigma. So this is what actually drives the lensing probability. Sigma to the power 4 tells us how massive the halo is, and dnd sigma tells us how abundant the halo is, and their combinations actually drives the lensing probability. And we can see that for lower sigma, as the dark matter is becoming more warmer, they are becoming less efficient lenses. So what is the expectations? The expectation is that there are less number of structures. The lensing overall lensing probability should be reduce, and also these low mass lenses causes the low time delays. So you should see the absence of low time delays as the dark matter is becoming more warmer. This is what you see when you get the time delay distributions. So as the dark matter is becoming more warmer, we can see there is a suppression of the lower time delays. This is the full time delay distributions. Now, if we consider only 10 years of observations, we cannot observe beyond 10 years the time delays which are greater than 10 years. So this is the observable time delay distribution, and you can see there is suppression in the low time delays. And this is how the overall the total number of expected lensed events changes or reduces as the dark matter is becoming more warmer. So MWDM infinity is the CDM limit. So I'm plotting with respect to 1 by MWDM. So 0 is the CDM here. So now let's say if we have n number of lensed event detections, and so we can get the time delay distributions, and we know how this time delay distribution varies with respect to the dark matter particle mass. So we can match those, and then we can get the constant on the MWDM. So we do it in a Bayesian analysis way. Now let's say let's consider true nature of the universe is CDM, and we simulate n number of lensed events, and then we try to match with our templates or the model time delay distributions. So, and the expectation is that the match should be higher towards the CDM side, low value at the CDM side. And if we consider only the number of lensed events, this is the constant. And if we consider the time delay distribution, the blue one is the constant and black one is the combined constant. So this region is the only allowed region, and this region is ruled out with 90% credible interval. So this is for 5 into 10 to the power 5 per year merger rate, which is optimistic. So it says that it can rule out basically MWDM less than 28 keV. Just to remind, current constant is MWDM greater than 6.08 keV. So this constant is like three times better than the current existing constant. And so we consider also pessimistic merger rates like 1 into 10 to the power 4. So even with the pessimistic merger rates, we can rule out MWDM less than 11 or 12 keV, which is also better than the current constants. This is for a particular realization, and if we do this test again and again, so these limits actually changes due to the Poisson fluctuations. So we expect the constants would lie within this shaded region, which is for different observation time period. So now the constant constant on the MWDM to the fuzzy dark matter, that is the wave-like dark matter, just simply equating the mass scales, half mode mass scales. And the current constant on this fuzzy dark matter is around greater than 10 to the power minus 22 electron volt. And we are getting kind of 3 orders of magnitude better constant. Just to conclude, if we consider a optimistic merger rate, then we can rule out around MWDM greater than 28 keV, which is essentially says that at those masses, the warm dark matter is not really warm. This is CDM. And if you consider also pessimistic merger rate, the modest constants are actually better than the existing constants. So there are inputs like source distributions where we will get from the unlensed events and lens parameter distributions, observational inputs, and the theoretical inputs like Helmholtz functions. Few caveats. So we neglected the selection function of the detectors, which is a true assumptions for the 3G detectors. And we consider a simple lens model SIS, which only produces 2 images. There are more complicated lenses which can produce more than 2, like 3 or 4 images. And the FWDM constant I show that is just a simple translation, and the proper analysis should be done like in Helmholtz function, considering the Helmholtz functions, and effects on the lens profile should be also considered. We also, and there are also other factors like cosmological parameters also changes the timeless distributions. So we check the correlation in the cosmological parameters, and we don't find any such correlations. And also like the core, WDM suggests some core in the central region. So we also check whether there is a degeneracy with the core radius, and we didn't find that results doesn't change significantly. I'll stop here.
Okay, thanks, Souvik. Questions? Anyone? Yeah, Loga, please.
So, like this kind of analysis, you think it can say things about this core cusp problem and satellite problem and so on?
Yeah, so we consider the core, we have done the same analysis using the core also. So I'll show the results. I haven't shown the results here. So, but the problem with this analysis, the thing is that we don't know how this core radius varies across the redshift or across the MWDM. So we took some parameterization which parameter fits the simulations, like this core radius, this ratio of the core radius and the virial radius, which goes like this, and we do the same test. This is what we get, the constant we are getting. So there is a potential to measure the core radius from this analysis also, but this needs to be revisited again.
But and what about the satellite? For example, if you had like a lot of satellites, is there a signature at in the gravitational waves lensing?
Yeah, so if we have like the more number of satellites, that means it is not special for the Milky Way. It's not special for the Milky Way. It should happen for all over the universe. So we'll get like more the time delay those are absent in our for the WDM, they would fill up. So from that we can consider.
Okay.
Any more questions? Okay, if not, then let's thank Souvik.